The place I live, the community I live in Bangalore, we used to give the collective waste in a pipe to the nearby lake. We had to do something about it. It's not right. You can't dump the waste to the nearby lake. And I can't complain because I live near the lake and the lake catches fire. You won't believe. It lasts 14 hours. 14 hours the lake burns. We call ourselves EcoSTP, Eco Sewage Treatment Plant, which is nothing but the good old septic tank compressed in a series of tanks together. It's got no moving parts. So the water flows from one chamber to another chamber. Cow stomach is a great model. So cow stomach is a great anaerobic bacteria machine, so to speak. Anything the cow it does, even cellulose it can treat, it can convert to, unlike a human stomach, which is all enzyme based. So we learned a little. So you put bad water in, you get good water out without using any power chemicals, no moving parts.
Welcome to Mindful Businesses, presented by Sarani, and I'm your host, Vidya Iyer. In our podcast, we bring to you brands that are mindful in their practices and processes. A mindful business adopts and employs sustainable social, economic, and environmental practices. Today, we have with us Tharun Kumar, CEO and founder of EcoSTP Technologies. Zero power, zero chemical sewage treatment technology. Welcome, Tharun. He joins us from Bangalore, India.
Hey, Vidya. Good morning. Glad to be here.
Yes, I'm excited to learn more about your company. So, how much sewage goes untreated, say in the Indian context or worldwide or in the United States?
Oh, there are various numbers, but around 93% is untreated in India.
Wow.
It's huge number, right? So we have a Pollution Control Board of India. They measure the track. As per them, we have 26,000 MLD, million liters per day of sewage, and 6,000 MLD is treated. Around 80% is their numbers, but 93% is usually is the number. But it's not only India. As for United Nations, say 80%. I was so surprised to read that number. 80% as per UN is discharged to the environment without any treatment. So it's not only an Indian issue, it's a global issue.
So where does it go? It just goes into our rivers and waterways, basically?
You look at India, it goes to water bodies, nearest water bodies, like in cities like Chennai and Bombay, we have the big sea. So it all goes to sea. And place like Bangalore, it goes to lakes. And also, sadly, it goes down to a groundwater. It infiltrates down. So that's a sad thing because many developing countries like India and other countries, we live on the groundwater, the borewell water, what we call. So that is getting contaminated because the sewage that comes in. So we have E. coli and other chemicals. E. coli is bacteria and other harmful chemicals in the groundwater, which is a riddle, right? How can a bacteria go all the way down, crossing the Vador zone and hit the groundwater? But that's a sad reality. That's the situation we are in now because we can't treat it.
And the groundwater pollution also then it seeps into the products that are made, right? So say you use the groundwater to make cookies or, some other eatables. It's not just the ground that is contaminated. It's the outputs which use the water that are contaminated.
We just put bore. We just dig out and just suck out the water from the ground. So most cities, we live on groundwater. So the water we get is not good because of the contaminated water that goes back.
The municipalities in the United States, they are responsible for treating the sewage unless you have your own septic tank and then you're responsible for treating that sewage. Who treats the sewage in India?
It's a mixed scenario. The municipalities also treat sewage, but they're not able to cope up with the urban population. To give an example of Bangalore, the municipality can treat waste from 4 million people. Now we are hit 14 million, 1-4. So the government says, guys, I can't do this. It's up to you. You are the polluter. You pay. You fix your problem. You polluted the whole thing. You put your own STP. I can only handle 4. Rest you have to treat it. So every housing unit by law has to put an STP, sewage treatment plant. And the housing units, they don't know how to do it. It's all normal guys. It's very complex machinery and need lots of power, chemicals, right? So they just can't do this. So some smart fellows, they manage to put an STP or sewage treatment plant. Rest can't do this. It's a very complex job to be done by trained experts, ideally by the government or the municipality, not by the end users. But unfortunately, the work is pushed to the end users. So they do this and they don't know how to do this. So two big issues. One is power issue and then it's a complex machinery. And usually they fail and then they let out to the water bodies and obviously there's no policing.
How do housing complexes, housing compounds treat the sewage that they generate?
Traditionally, it was much more dispersed. We're not concentrated into one particular location, right? It's all dispersed. And we had small pits called septic tanks, which does sewage. And they treat to some extent. So our tech is based on anaerobic bacteria. So anaerobic bacteria lives in a septic tank. That's how nature intended to treat sewage to some extent. But now it's all compressed to a small location and everybody is putting sewage into one place and just completely collapses. That's how nature treats. And if it's distributed, yes, even if you throw all over the place, the earth will filter it out, there'll be some sunlight coming in. There are 100 ways the nature will decompose the waste. There's centipedes, millipedes, so many things will break down the waste and then that's how nature intended. But now, if you have 14 million people in a small location, then it's a disaster.
The homeowners who have septic tanks, they put bacteria in it. So what kind of bacteria is that they put?
They usually put anaerobic bacteria that decompose the waste to some extent. It's a small box. So what we've done is we've taken the same concept to a different level to make sure it treats in a much smarter way. But it's a good old concept, the good old septic tank concept which we've taken. And it works well if it's in a distributed area, but you can't do the whole thing in a compressed manner.
So the other thing that they do here, at least in my municipality, is that they take the solid waste which come out of sewage and use it for biogas plants. They create energy out of it. Is that done in Bangalore and other places?
To some extent, because it is the gas that comes out is come from the sewage. So the cultural issues of using the gas. The calorific value of the gas is low, which means you won't get too much heat from this. It's good for some slow cooking. In India, we call slow biryani. It's good for it. It's not very popular, so to speak, so it's let out.
I guess there's no one absolute solution. All solutions have to work in partnership. The municipality has to do their part.
Yeah.
The biogas folks, the people who are just doing the anaerobic digesters. So tell us about yourself. How do you fit in this solution?
We call ourselves EcoSTP, Eco Sewage Treatment Plant, which is nothing but the good old septic tank compressed in a series of tanks together. It's got no moving parts. So the water flows from one chamber to another chamber through multiple pipes.
Tell us where Tharun Kumar fits in this solution. What is your background?
I was in a different field. I was in IT, a long story, but I started with IT project management, right? Worked in companies like Q Software, Motorola. In fact, I was in Virginia for a couple of years. Happy software guy, I was. Then I moved into I did a program in IIM Bangalore and I moved to business, like knowledge management, innovation management, those things I did, right? So I did a complete career shift to I don't want to be known as a techie. Right, so I moved there. Then I was got bored of business. I said I'll do something different. I do cyber security. So I moved to cyber security. I did a few years on cyber security. I set up Aadhaar scheme. Plan is the largest biomedical scheme. So we did that. And then I switched to last 8 years. I'm in deep shit, so to speak. I moved to environment science. So last 8 years I'm in this. Yeah, so that's how completely different sets of portfolios we did on my career.
What was the moment that you transitioned from an IT professional to sewage treatment? How did that happen?
The place I live, the community I live in Bangalore, we used to give all our waste, collective waste, in a pipe to the nearby lake. We all dump all the waste to the lake. That's what we're doing. So we thought we had to do something about it. It's not right. You can't dump the waste to the nearby lake. And I can't complain because I live near the lake and the lake catches fire. You won't believe. It lasts 14 hours. 14 hours the lake burns. And why lake burns? Because there are 400 mld waste coming every single day and that just burns.
How far is that lake from your home?
Half a kilometer from my place. Not very close, but it's impacting everyone around this stuff.
These homes are about $500,000 or more, upper middle class, professional Indians who live in these homes who are dumping the waste, which is going into the lake.
It's all high-end villas. It's a place called Whitefield. It's all upper middle class areas. We all dump it to the waste. And We know we are dumping there, but we never knew how to fix it. We are busy with our own world and we just move on with life. So I said, let's do something about it. Let me see, is there any other way out? So we said, how do we fix it? We went to the municipality. Municipality said, you have to put a STP by law. You're not done it. You're dumping the waste. It's your job. No, I can't do it. The same story. I can do only 4 million. Now you become 14 million. I can't do it. It's your job to go and fix it. So we said, okay, let's start with the STP, sewage treatment plant. So what we found is the STP, sewage treatment plant, what you get in the market, there are a lot of complex machinery and needs a lot of power and need operators. Skilled operators, complex machinery, and lots of power. And they all work on a principle of blowing air through fecal matter. So coming from IT perspective, I was a little surprised. Right? I thought there's some other tech. Everybody's got the same tech. Big companies, small companies, blow air through fecal matter and add a bacteria every 1 hour into the system. So one guy says, no, sir, we don't do we do 1.5 hours. So I have a smarter way to add bacteria. They use a word called MLSS process, RAS process, very high-end technical jargon. But when you break it down, it's all about adding bacteria every 1 hour. And whatever clear water you get, you sieve it out. So they have a filter. They call charcoal filter or sand filter, and then they sieve it out. And then the sieve, you have to throw it away. And where do you throw it away? No, sir, you throw it away somewhere it is, right? That's a tech. Unfortunately, this is a tech across the world, right? Even now, last 40, 60 years, that's what we're trying to disrupt. The same tech everywhere. You look at it. It's okay for a municipality to do this. They know how to sieve it better. They know how to do it better. But for a housing society, residents to manage this was a little complex. So we said, okay, can we do something else? How did nature treat this? So nature, like you said, it is septic tank derived thing. So can we improve the septic tank to make sure that the entire residence waste can be treated? So we did some work on it. So I left the company. I joined an environment consulting company to learn more about it. So there are a lot of companies to learn this. So I learned this. I started deploying in my own locality, the so-called eat your own dog food. Got it working to some extent. He improved it. It took some 4 or 5 years to improve it to the level where we are in today. That's how the story started.
That's pretty incredible. You mentioned nature cleans up waste. So how did you learn from nature?
When you look at nature treats waste by original waste by septic tanks and other units. And septic tank works on anaerobic bacteria. So anaerobic bacteria is what treats what's in septic tank. So we studied a little more. What the hell is this anaerobic bacteria? How does it treat, right? Normal STPs work on aerobic bacteria. That's why you need air. So aerobic, anaerobic. So anaerobic doesn't need air. This is how nature always used it. And anaerobic bacteria which found was there before even we all came. That was one of the first organisms. There's not even hair. Those days, it was there, and then it improved, and that's the one who breaks down everything. And what we call as decomposers, right? The big decomposers who are like millipedes and worms and all, and the small ones. These are the ones who break down everything from nature to a small unit. So we said, how do you make this anaerobic bacteria work better to my concentrated waste? You have entire community waste coming in one tank. I have to make sure that it's able to decompose the whole waste that comes in. So we worked on a smarter bacteria. And then cow stomach is a great model. So cow stomach is a great anaerobic bacteria machine, so to speak. Anything the cow, it does. Even cellulose it can treat. It can convert to, unlike a human stomach, which is all enzyme based. So we learned a little bit from cow stomach, how do you do this? And then we applied for a mentorship with the Biomimicry Institute based out of US, Montana. Me and my friends were there a couple of times. We learned a lot from them how to do this. So improved lots of ideas across the world we got, and that's how we reached the product this level.
So what is biomimicry?
Biomimicry is simple learning from nature, mimicking nature. You learn from nature. Little more technical, mimicking nature plus use an organism to get a function. So we do both. We mimic a cow stomach and also use anaerobic bacteria to make it work. So that's it's a true biomimicry innovation.
And the cow has 4 stomachs.
Yes, cow has got 4 stomachs, yeah.
And your solution has 4 tanks.
Yeah, 4 tanks, yeah. So the first tank collects everything, but cow it takes you to the mouth and it cuts out and makes it into smaller bits, which we don't do because whatever flush down is anyway a soft thing, what it flush down. So it's okay. So we move from one tank to another one, and we as much as possible. For example, cow stomach is full rough because of fillet, small fibers. That's how the bacteria lives. So we try to make it all rough plastering. It's all very rough surfaces. So we increase the surface area. So we did all these simple things, old techniques, moved it together. So we put bad water in, you get good water out without using any power chemicals, no moving parts.
Describe each chamber to me. Do you call it a chamber or a vessel?
We call digesters. We call RDF1, RDF2, RDF3. Rumen digester filter 1, rumen digester filter 2, and 3. 3 filters in the main tank. And last one is a constructed, it's not really a cow thing, but it's a constructed wetland which we improved it along with a slow sand filter. I'll talk about it. So 3 tanks, tank 1, tank 2, tank 3, or we call rumen digester filter. So each has got its own purpose, how it works. And the beauty is, if you little bit deep on how anaerobic bacteria works, is amazing. Usual example is if you put a sugar, how the ant comes, right? The ant come to eat it up. So same, some kind of cosmic intelligence. So there are 4 sets of bacteria, not one, which decompose the whole waste, whatever you flush down.
How often do I have to add bacteria in your solution?
Only one time. Initially, in the bottom we lay a layer of fresh cow dung and we apply a bacteria. It's again from cow stomach. One time we do it, you close it, we don't touch it. We remove the sludge once in 2 years, digest it. Otherwise, nobody should touch STP. That's our design goal. No one should touch STP for 2 years.
Why do you not have to add bacteria every hour or hour and a half in your solution?
Because the way we construct it, first of all, we don't want to touch, let it run on its own. We don't want to add bacteria, then maintenance comes up. So the way we designed, we put a bed of cow dung in the bottom, and then as soon as someone flushes the waste, bacteria keeps on hibernating. So if more waste comes up, the bacteria becomes more, 2, 4, 8 like that, or it hibernates and goes down. That's how it works. This is how the innovation. So we don't have to, if you want, we can say, I can keep on adding every 1 year, I can top up the bacteria, but you don't need all the stuff. Right? So this is how nature intended.
They were blowing air to get the oxygen, and in your bacteria doesn't need that.
That's right. Every STP across the world use aerobic bacteria. We use anaerobic. So this is the fundamental differences between these two. And that's why we're trying a lot to concept sell anaerobic bacteria, because it's got a kind of bad PR, because no one uses anaerobic. They use what called septic conditions, so bad, smelly. We're trying to say, guys, this is something different, this is something unique. And if you know, I'll take a minute to explain how the bacteria works. Is anaerobic bacteria, you put a waste in a septic tank anywhere else, or a cow stomach rather. There are 4 sets of bacteria that comes up. So first is we call hydrolysis stage. There's a hydrolysis bacteria, they come. They break down, so whatever you eat, the carbs, what we flush down is all carbs, protein, fat, right? So that comes in soft material. They break into simple components. So that's all it does. Just break it down to simple components. It makes into sugars, amino acids, the first set of bacteria. Now, strange. It's like a relay race. Once this guy has done the job, the second set of bacteria called acidogenesis bacteria, they come in. They convert it, break it down, and they make it into small, it's like the milk eating sour, same concept. They break it on to much more smaller one. Technically, they make it to amino acids, short chain acids, it's all jargon. So break it down. And once those two have done the job, then the third guy called acidogenesis bacteria, another set of bacteria, they break it down into acetic acid, CO2, carbon hydrogen, they do it. And once these 3 have done the job, then the hero comes in called the methanogenesis bacteria. They're the most hardened anaerobic bacteria. They come and convert and do the rest of the job. So what happens is, you put bad water out, clear water comes out at the other side, and with gases coming out a little bit. But this is how nature intended, right? This is a beautiful system, right? So we're trying to make it work. How do you make sure these 4 teams work together so well and make sure that they work in harmony? That's what we're trying to do. But it's amazing. Whereas aerobic bacteria, you completely scrap this concept. You put in a box, you just blow out through fecal matter, which means you need a blower motor, you need power, and then it works. Separately, manually add a aerobic bacteria in a process called RAS or MLSS, and that also works. That also both gives the same output. But this is unnatural. And last 60, 70 years, no change in technology, the same tech. So we have technology known as moving bed bioreactor, sequential batch reactor. Any name you take, the same damn thing, right? Blow out through fecal matter and add bacteria one up, and using a filter and sieve it out. Now you have much better filters. You have much better sieves. But end of the day, it's a sieve. You are not treating it. You are just taking this, and you have to throw away the sieve, whatever, you have to throw it away. If you took a slow sand filter, which treats waste, it filters the waste out. If you look at the constructed wetland, the roots, they remove the waste. This is how nature intended. So we're trying to bring back all these old techniques into one solution in an urban scenario. Because at the end of the day, it should work. It should work in a Bangalore or a Chennai or Delhi.
This is buried underground.
Underground, that's right, yeah.
No air blowing through it.
No air blowing through it, yeah.
How does the sludge move from one chamber to another?
The sludge doesn't move. Sludge lays in the bottom. So let me sludge lays in the bottom. Tank number one, everything settles down. Water flush down, the bottom. And the bacteria is living in the bottom, eats up all along the bacteria, eats up. And then you are flushing more water is coming in. So water has to fill up. The good old Archimedes principle. So water goes up to the next tank via few pipes. There are a series of pipes. And the water from the pipes, it goes way down to the bottom, not to the top, where the next layer of bacteria set is living. So feed the bacteria and then they get treated again. Again, someone flushes, again water fills up, it moves to the next tank. So a much clearer water goes to the next tank, again through a series of pipes. So it's all one-time job, you do it and then you don't touch it. And that's how it gets cleaned.
So this is how I'm visualizing it. You have tank number one. On the bottom, you have cow dung, which gives you your anaerobic bacteria. And the sewage comes in. It gets treated by the bacteria on the bottom. Clearer liquids rise up. You have pipes starting at the top of the tank number one, which kind of skims the water and puts it at the bottom of tank number two.
That's right.
And then the process goes the second time. Does tank number two also have cow dung, or how does that work?
Yes.
And then it goes to the same process, tank number 2 to 3. So you have to do it 2 or 3 times.
Yeah. By the time the water moves from stage 2, it's a visually clear water. There's no sludge. It's a very clear water. It's slightly yellowish, but clear water. Then we move to stage number 3, the last stage of opomasum, the last stage of the cow stomach. What we done here is we fill up the tank with the gravel, it's normal good old gravel, and we supply some recycled plastic materials with a lot of surface. It's like a ball with lots of hole inside. So we mix up with the gravel and fill it up. And water and the bacteria is living in the edge of the walls or the gravel, the anaerobic bacteria. So there's a third stage. So, and the water flows through the gravel and the bacteria is eating up whatever comes in, whatever little bit on, and then you get clear water out. So by third stage, we have completely clear water comes in. Extremely complex process, but very simple to execute.
You also have eliminated the use of electricity and power. You let the sewage stay in each container for about 72 hours for the bacteria to work on breaking it down.
That's right. That's right.
And you use basic physics to move the water from one chamber to another.
Physics, yeah. By gravity, it flows from one to another one. And the gravity is a huge power, right? That's a world's most known power, the most powerful force what we have. So we just use that power to move the water, and then when it fills up, it has to go to the next tank. How it goes? By gravity, there are pipes attached, so water spills to the next tank through the pipes, and we just smartly made sure that the water spills down to the next tank, goes down through the pipe to the bacteria's mouth, so to speak. So the bacteria gets the food and then it spills over. So it's simple technique which we've done smartly, a clever design, so to speak. Since you are only flushing slowly, it slowly moves from one tank to another one. And it gives time for the bacteria to eat the food. So we hold the whole water for something like 72 hours, the whole water. The bacteria gets 72 hours to clean up the muck and clear water comes out. And tanks can be any size. So it can be L shape, B size, and around the building. And that's how we do it. So tanks, these are large tanks. We need more space than a normal STP. But we do it underground wherever space is available.
So did you make a small prototype, like a table-sized prototype, before going and digging a pit and doing it? Or
we can't do this, unlike a normal product, I can't do this prototyping and I can't iterate. We actually did a safety tank. We improved on it. We took the water quality before and after. We added one more chamber, one more pipe, and we got it all working. And there are similar models also around the world. We learned a lot from them, and we put it all together. And we have got a lot more support to do this stuff.
So when we talk about sewer water, you're talking mostly only about waste from households. Are you talking about rainwater too, or?
No, it's only household. Whatever you flush down, your bathing water, your washing machine water, everything, whatever waste home generates is what we can treat. We don't do chemicals. Let's say effluent treatment plant, which we don't do. We do only human waste. And that is a big issue.
The reason I asked is in our town, Lafayette, Indiana, what they do is instead of having storm drains where the water goes into the gutters and then connects to the river, they have rain gardens. And where the water goes, and they have particular plants in there which actually filter the water and reduces the impact of the water going from the city drains to the rivers. So does your solution have some component of that, or?
Yeah, we do that. When I say stage 1, 2, 3 underground chambers, water gets cleared. Then water comes out. We run through the same system what we are using plants. So again, a bed of gravel with some few plants on top of it, and water flows to the roots. And they do the further cleaning. And that's again a good old technique, the good old constructed wetland technique. The plants run the oxygen, it leaks oxygen to the root rhizomes to the water and get treated. And so that's how the water gets treated. So plants treated a little bit. It also got a built-in a technique known as slow sand filter. It's again an old technique. It's like I'm told that is a 150-year-old technique. It's amazing. I mean that system. Like it's a sand bed, and the top natural filter is formed naturally. Right? This is how nature treated. It's a cocktail of algae, protozoa, planktons, bacteria. It's known as Schlumtech. That's a technical word. It's a filter skin. That treats. In fact, that slow sand filter is known to remove heavy metals, viruses. Like imagine nature system can remove heavy metals, viruses. No one tested, but no one uses this. It's all old technique. Everybody wants now is compact, push the button. No? So we use the slow sand filter along with this constructed wetland. That's how we get a crystal clear water output. So we have some Instagram pictures wherein the water is as visually super clear like any bottled water, as good as it, because we do this natural process.
If you've tested your water, how would you compare it to, say, drinking water or STP, traditional STP, treated water?
Yeah, so we designed this to comply to the norms of the country. So it's not drinking quality water. There are two parameters which we here check here. It's mostly globally the same thing called BOD and COD. So two parameters. BOD should be less than 10 and COD be less than 50. So that's what we comply with. And there are 4 or 5 parameters more, but this is the primary, the 2 parameters. Now, this water, what you get in is clear water. If you want to use it for drinking, you can put additional filters. In fact, we are done for one of our clients. This water that you get, clear water, is better than the water you get from some other source. So we put a commercial reverse osmosis system to treat to a drinking quality water. They're not drinking, but they're using for bathing because still mindset issues. But money spent is only for the last stage RO system. Up to here, it is completely natural. This classic toilet to tap, we got it implemented for one of our clients here.
So what is the capacity of your solution? How much sewage can you treat, or do you have it in different sizes?
We have different sizes. So the smallest size we call 6 KLD, kiloliters per day, or typically 10 houses, 10 homes is what we can treat today. And the maximum is 1000 KLD. It's typically 4,000 homes.
How much space do I need in the ground? Like in these areas, real estate is at a premium.
Yeah.
How would you find the space?
So this was a big challenge for us because this anaerobic systems needs more space. And space is a premium, right? So what we've done is we typically need 28 KLD, kiloliters per day. So 1 KLD, we need 28 square feet of space. So this space we find out in the basement area of the building or a road or a children's playground or around the building. setback, somehow we find a space because we designed a solution. It's like a wax model. It can be any shape. So some places have only 1 meter width and a long one. I run the STP along. We find a space. So this how we are unique. We can really embrace. So that's why we call biophilic. When a new building coming up, wrap it around the STP along with this so that you're done with this when you make a new building. It's not easy to build for our old buildings because I won't find space. But a new housing complex coming up is pretty easy.
How much does it cost?
We have two costs. One is we sell a license. We don't make the box. So we call a kit. That way is more sustainable because I don't make the box. So it's made locally. So we sell a license and the civil cost. Civil cost is the biggest cost. Say 80 to 90% is civil cost. So civil cost will cost around 50,000 rupees per KLD. So around $600 per KLD. That's the cost of the civil.
When you say civil, you mean the construction of the box.
Yeah.
And it's made of concrete.
It's made of concrete. So then you can just add on to it. More space, more capacity, more things. So you keep add on to it.
So you said about $600 per KLD. So your biggest one is 1,000 KLD, which treats about 4,000 homes.
Yeah.
So even the largest one is only about $600,000. We are assuming there are no economies of scale. So, and that treats about 4,000 homes. So, and this is a one-time cost.
That's the key thing. It's a one-time cost. You're spending the money only on this cement, steel, labor, and sand, 4 or 5 items. So if you're a new developer, you're making a massive building. So he may have a way to get a cement at a lower cost or a sand at a lower cost. So it goes along with that thing. So that's what we have. Our target customers are now new buildings coming up. I say, guys, though it looks big money, it's end of the day, it's only cement, labor, sand, which you expert in this. You buy the license from us and you just go and do it.
What I like about your solution is that you didn't innovate one or discover one of these solutions, but these solutions existed. You made it in a form which is affordable, scalable, and gave you the output in a very eco-friendly way.
That's right, yeah. Like I said earlier, we have people to help us out. I said Biomimicry Institute, they helped us a lot. In fact, we got won a small award. We got some $3,000. So $3,000 was a lot of money in India when we were starting a company. So we started with that. We hired some engineers with that money. Then we have a Royal Academy of Engineering, London. We got a fellowship from them. So they helped us a lot. So we are doing a good thing. So a lot of good people across the world are helping us out. Shelter Tech is a Habitat for Humanity. They helped us out in an accelerator program. And later they invested in a company because they helped us out. They saw us working. Then lastly, we come from corporate. So we know that how a great a tech is, unless you know the customer psychology, you can't work. Not domain knowledge. So we have a brigade group from Bangalore who are helping us out. So they are the accelerator for us. So we use their office space, their premises. So we got domain knowledge from them. So all of this put together is what we reached where we are in today.
How big is your team now?
14 members, 14.
Do you have multiple investors or is it your own source of funding?
In our own source of funding, but we have one investor, Habitat for Humanity. We took a small money from them and we had a choice to go to many investors, but all of the investors, as you know, they're all 20x in 3 years, 4 years angel investors. We said, I want to go to impact investors. So we went to Habitat for Humanity and we took a small funding fund. But we are self-sufficient. We make our own money. We are a profitable enterprise, though small money, but still we're making profit. We make money. And we also show a big purpose because that's how we attract talent. So, for example, we have a colleague, Prasid. He was running lots of product management operations, very good in operations. He joined us from another person called Lokesh. Lokesh, he was I don't know how to spell out, Anheuser-Busch or something.
Anheuser-Busch.
Anheuser-Busch, yeah, we call him Budweiser. So he was 6 Sigma Master Black Belt, head of quality. I said, what are you doing? How you worried a beer? Come and pure the water. So he left the job and joined us. The purpose is so big. Another person, Ramya, she was handling the learning and development for Just Dial. It's the largest telemarketing company. I said, come over, help us out, right? And she handles customer success. So she comes and joins up. And recently, I was trying to attract salespeople, and salespeople, they never likes purpose. So they're very clear. No purpose can attract them. So our sales head, Amar Patel, so he joined us he was joined a fintech company. I said, how long can you sell fintech, right? Come on. It's a huge purpose, and we know a product that works. And he joined us. So able to attract the great talent. And of course, we have a good technology, and we pull it all together. So I'm only collecting all together. That's it. You don't need to do any great innovation on the space here.
So you said all these people are joining you because the purpose is so good. But what is the impact of EcoSTP?
So what we do is we measure the impact real time and we display it on our website. So it's very tangible. Yesterday we treated 450 million liters of water, sewage, right? 450 million liters. It may be a small number, but more than the water is the power that's saved. 75 megawatts of power we saved. It's a big number. And then we translate that equal to powering 124 villages for a whole year. So that kind of power we saved. And if you look at India, we are running out of coal. Next 2 weeks only we have coal. So that much power we are saving. And these are nice, tangible numbers, audited, but this is what drives the entire team. So huge purpose. So what we say is average pay, huge purpose.
That is an inspiring story. Thank you so much, Tharun. It was very informative how EcoSTP uses the knowledge that it's gained from nature to solve our environmental problems. Thank you again.
My pleasure. Enjoyed it.
You're listening to Mindful Businesses, hosted and produced by Vidya Iyer. We'd love to hear your thoughts and feedback. If you'd like to send a question or a comment about this episode, send us a voice note to info@mindfulbusinessespodcast.com. Rate and review us on Apple Podcast. If you learned a thing or two from this episode, share it with one friend. We recorded this podcast in Lafayette, Indiana. Theme music was composed by Tatum Gale. Our marketing assistant is Caitlin Milligan. This is Vidya Iyer with Mindful Businesses.